Today I will explain the thermal stress analysis in Autodesk Fusion 360. So we have already explained the static stress analysis. So this is a tutorial on thermal stress analysis. So this is the thermal stress analysis. So here you can see that there are two types of analysis: thermal analysis and thermal stress analysis. So here we are dealing with this one, thermal stress analysis. Okay, so this tutorial shows how to modify geometry on a simulation model. So you can use symmetry to save time and effort. So here we are using simplify to simplify the our geometry such that we can save our time and effort, that is with the help of the simplify environment. So I will explain this later. You create an eighth symmetry simulation model from a full model of cast iron disc breaker rotor that is larger than the ones used on cars and trucks and is used for heavy or industrial equipment applications. You determine the pressure and temperature induced stresses in the 1/8th variant of the disc brake rotor model and practice interpreting the results to see if the rotor yields to applied loads. So here in the tutorial we will explain the create a thermal stress study to determine the temperature, pressure induced stresses in a disc brake rotor. Then eliminate geometry that is irrelevant to the analysis in the simplify environment. With the help of this simplify environment, eliminate the geometry to reduce, what is the purpose? To reduce the analysis time. Then apply constraints on 1/8th symmetry plane faces to fully constrain the free body movement of the model without impeding the expected thermal expansion. Apply pressure and thermal loads to represent the experience of the brake rotor during use. Solve the analysis and examine the safety factor, stress, displacement, heat flux, thermal gradient resulting from the combined mechanical and thermal loads. So this combined mechanical and thermal loads, though it is called a thermal analysis, to determine whether the brake rotor yields as a result of the loads. Okay, so here you can see this is the this is the full model. This is the full model of the disc brake rotor, and this is the 1/8th model of the variant. Okay, so we will you can see there are different activities in tutorial: activity 1, 2, 3, 4, 5. So we will do the first activity number 1. So here in the activity number 1, we go to the activity 1 summary. So here in this activity you have to switch to the workspace to create the thermal stress study. Then change the default stress free temperature to 25 degrees Celsius. Then set the mesh size to 6 mm. Then verified the custom units system settings. Then checked that the model material was properly assigned. Okay, so these are the summary of the tutorial activity number 1. Okay, so we will start with so this is the step 1. So here first we have to open rotor. So first you have to open the brake rotor from the basic training folder in the data panel. So we already explained how to open a geometry from the data panel. Okay, so I will open it. Okay, double click the brake rotor to move on the canvas. I will show it. Okay, go to Fusion 360. Now you can see this brake rotor in the screen. So go to the home tab. Then you can see in the home tab you can see okay, so in the home tab you can see basic training tab. This is the basic training tab. Okay, double click here. So I will double click here. Then in this basic training tab, you can see the number 11. Okay, simulation. Okay, so go to number 11, simulation. So this is the number 11 simulation. Double click here, this one, double click the simulation. Okay, so in the simulation tab you can see different types of geometries. You have to double click on the brake rotor. You can the brake rotor, double click on this one. You have to double click on this one, brake rotor. Okay, then you can see your brake rotor will be opens in the design workspace. So this is the design workspace. Okay, then I will close this. Then I will change this design workspace into simulation workspace. So this click here and go to the simulation workspace. Click the simulation tab. So now the workspace is actually changed into simulation workspace. Okay, so you can see this is the workspace. So this is the simulation workspace. Okay, then I will, so now rotor is in the simulation workspace. Then next is you have to okay, so here we are each type of analysis. We are planning to conduct the thermal stress analysis. Okay, so for a few seconds. Okay, so you can see this. So you can see the new study in the simulation. You can see new study. So here you can conduct static stress, model frequency, electronics cooling, thermal analysis, thermal stress, structural buckling, nonlinear static stress, event simulation and shape optimization. So here we are conducting the thermal analysis. So you have to select this thermal analysis. Okay, go to the simulation workspace, then select the thermal stress. Okay, here you can see in the thermal stress, determine temperatures and stress distributions on the model resulting from both thermal and structural loads. So here the loads are both thermal and structural loads. Okay, click the create study. Now our study is actually thermal stress. So you can see in the browser tab, you can see study number 1. You can see study number 1, thermal stress. So thermal stress is actually activated. Okay, then we have to save this. Okay, we have to save this file in any one of the folder. Okay, then we have selected the thermal. Okay, then the next step is change the default stress-free temperature to 25 degrees Celsius. Okay, so that is the next step. And another one is the mesh size. Set the mesh size is 6 mm. Okay, then I will go to the, so here I will show you. So here there is a tab called manage tab. Okay, so here there is a tab called manage tab. So you have to click this tab, manage tab. So go to manage tab settings. Okay, then you can see the study type. So the study type is actually thermal stress. Select this thermal stress. Then you can see default stress-free temperature, that is 25. Then go to the mesh tab. The absolute size is 6 mm. Okay, then the next thing is verify that the custom unit system defined as listed in the following table and change any that differ. So length mm, mass kilogram, time seconds, force newton, pressure megapascal, temperature Celsius, energy joule, power watt, acceleration meter per second square, angle degree. Okay, so in the browser hover the units, then click edit, then settings, choose custom in the default unit set, then compare the unit settings with the table and change any that differ. Click OK to accept the change and close the dialog. Okay, so we have to check this table with our units. So here in the browser tab you click the custom units, so you can see you can select metric unit, inch, US unit and custom. Okay, so custom unit. Okay, so check this table with here. So this is length mm, mass kilogram. Okay, you can see length mm, mass kilogram, then time second, force newton. Okay, time second, force newton. Okay, pressure megapascal, temperature Celsius, pressure megapascal, temperature Celsius, then energy joule, power watt, energy joule, power watt, then acceleration meter per second square, sorry, acceleration meter per second square, then angle is degree. Okay, then click OK. So that is completed. Then next is apply the material. Okay, so here once again. Okay, so here the brake rotor material is this one, iron grey cast ASTM A48 grade 20. So cast iron is commonly used for brake rotors due to the thermal characteristics of the material. Okay, so go to the simulation workspace, then setup tab, materials panel, study materials, then in the study materials dialog, the study material column, the material will be iron grey cast ASTM A48 grade 20. Okay, so go to the, so here you can see, the materials tab. So this is the materials tab. Okay, so from this, so click here, study materials. So click the study material. So here you can see this this iron grey cast ASTM A48 grade 20. Okay, so override. So I will override this iron grey cast ASTM A48 grade 50. Okay, then click OK. Okay, so in the browser tab you can see in the browser tab you can see the materials. Okay, iron grey cast. Okay, so it is here. Okay, so the activity 1 is completed. So here what we do is, first thing is we have to select the simulation workspace and then the select thermal stress study, then change the default stress-free temperature to 25 degrees Celsius and set the mesh size to 6 mm, then custom unit settings, then we have to apply the properly assigned the material. So tutorial activity 1 is completed. Then next is activity 2. Click here, activity 2. So activity 2 is actually simplify the model, okay, to create an 8th symmetry variant. Okay, so here you can see this is the full disc brake rotor model, and here this is the 8th symmetry variant model. Okay, so we have to simplify this because this is a symmetric object. Okay, so in this activity you use the simplify environment. So here there is a tab called simplify environment to create an 8th symmetry variant of the full disc brake rotor model. Changes made on the simulation model do not affect the production model and are specifically for the simulation purpose. Okay, so here we have to start with the first step. Okay, the first step will be I will show you. Okay, so split the body in half using the XY plane. So here we are using the XY plane as the splitting tool. XY plane is the splitting tool. Okay, XY plane is the splitting tool. Okay, so simulation workspace, setup tab, simplify panel, simplify. To open the simplify environment, first you have to open the simplify environment. Then simulation workspace, simplify solid tab, modify panel, then split body. To open the split body dialog box, then click the brake rotor to select it as the body to, so body to split. So this is the rotor, brake rotor is the body to split. Then split body dialog, click select to activate the splitting tool. Then you have to activate the splitting tool. Okay, then go to the browser tab, expand origin, and then click the XY plane. As I already explained, XY plane is the splitting tool. Okay, so click OK to accept the command and close the split body dialog box. Okay, so we can go to the simplify tab. So here go to the simplify, then so you have to go to simplify tab. So this is the simplify tab. Okay, now you are in the so here now you are in the simplify tab. Okay, I will show you. Okay, so here you can see, you are in the simplify tab. You want to simplify solid, you want to simplify solid. So now you are in the simplify tab. Okay, so you can simplify this model. Then simplify solid tab, modify panel and split. Okay, simplify solid panel, sorry, so click the simplify solid tab, then modify panel, yes, modify panel, split body, modify panel. So here you can see split, then split body. Okay, so here you can see this is the split body dialog box. So this is the split body dialog box. Okay, body to split, that is you can see the first one, body to split, select. So here select the brake rotor. So you can see one selected, body to split. The next is the splitting tool. Okay, as I already explained, splitting tool is the XY plane. Okay, so select this, then go to expand origin, okay, so click the arrow near to the origin. Okay, then you have to select which plane, the plane is XY plane. So you have to select this XY plane. Okay, you have to select this XY plane. Okay, then you have to click this. Okay, okay, so here you can see, this body is actually splitted into two. So here this is, so here in the model components bodies, here you can see this is body 1. So here this is body 1. Okay, this is body 1 and this is another body. Okay, two bodies. Okay, then next is you have to split the model again, and you have to using the XZ plane as the splitting tool. Okay, so here in the second thing, the XZ plane is the splitting tool. Okay, to create 4 bodies, then right click on the canvas and choose repeat split body from the top of the marking menu. Click and drag the mouse from the right to left and draw a selection window that intersects the two bodies. When dragging the selection rectangle in this direction, you do not have to fully enclose the bodies to select them. In the split body dialog box, click select to activate the splitting tool selector. Then XZ plane to select the splitting. So this is the splitting tool. Then click OK to accept the command and close the split body dialog box. Okay, so here right click here, right click in the canvas, Okay, wait for some time. Okay, so right click in the canvas. Okay, you can see repeat split body, so click here, repeat split body. Okay, then body to split, you have to select the this full. Okay, then the splitting tool, so splitting tool is XZ, this is the splitting tool. Then okay. Okay, now your body is divided into, so you can see. Okay, so next is the third step. Okay, so the third step is the splitting tool will be the YZ plane. So the splitting tool will be the YZ plane. Okay, to create 8 bodies. Okay, so right click here, repeat split body, then you have to select this brake rotor, then splitting tool, that is the YZ. Okay, so splitting tool is the YZ plane, then click OK. So you can see 1 2 3 4 5 6 7 8. Okay, then here you have to remove 7 of the 8 bodies. If you have changed the model viewpoint since opening the model, click home view above the view cube to restore the default isometric view. So if you want to see the default isometric view, you have to click this home button. Okay, this is the default isometric view. And simulation workspace, simplify solid tab, select panel, then selection priority, select panel, select panel. So this is the select panel, and then selection priority. So the selection priority will be select body priority. Okay, so select, then selection priority, select body priority. Okay, then click the segment of the rotor that is in the positive X, Y, positive Y, positive Z global quadrant. Then right click in the canvas and choose invert selection from the context menu. The previously selected segment is deselected and the other 7 segments are selected. Okay, so 1 2 3 4 5 6 7, okay, 8. Okay, then right click here, you can see remove. Okay, remove. Okay, so click simulation workspace, simplify solid tab, finish, simplify panel. You can see it's finish, simplify panel. Click the finish, simplify panel. Okay, so now you can see your model is actually simplified. Okay, with the help of the simplify tab. Okay, okay, so here the activity 2 summary. Okay, in this activity we have completed split the original body using the 3 global planes XY, YZ and XZ. Then removed 7 of the 8 derived bodies, leaving only 1/8 of the original body. So we have completed that activity. Okay, the next third activity will be the constraints. Apply the constraints. Okay, so in this activity change the selection mode to select phase priority to make phase selection easier. So in the previous activity we have select the body priority. That means we have to the first priority when we select anything, body will be selected, that is the select body priority. So here we are using select face priority, so you can select the face, okay, to make face selection easier. Practice using the different selection variations. Then apply fixed structural constraints on the x, y and z directions, okay. Then next is we have to apply the constraints, okay. So the first step will be, okay, first you have to activate the, go to the select panel, then selection priority, then go to select face priority, click here, select face priority, okay. Then here go to the structural constraints, then here this face you have to fix this face in the UX axis, okay. Make UX, click UX and UI to deactivate this axis, okay. So we have to go to the constraint, structural constraint, select this, you have to select this face and select this face, okay. So you have to select this face, then the selection, the axis will be UX only. So here you can see the type is fixed, target two faces selected, only UX, okay. Then you have to click OK. Then here in this opposite direction, in this, okay. So again go to the constraint in the UI direction, okay. So go to the constraints, structural constraints, select this face and select this face, then constraint only in the Y axis, okay. Then you have to select the 8 faces in this plane, in the on the XY plane, and constrain them in the Z direction, okay. Okay, so go to constraint, structural constraint, 1 2 3 4 5 6 7 and 8, only in the UZ direction, okay. Constraint in the UZ direction, okay. Then click OK, okay. Then you have to rotate the model, okay. So you can see you have to rotate this model in like this, okay. You have to rotate this model like this and select one of the 8 faces, okay. So here you have to go to select this one of the 8 faces, then go to structural constraint, go to structural constraint, go to structural constraint, the type is fixed, click UX and UI to deactivate this axis only, UZ is now active, okay. Bottom view of the cube, then window, select the top edge of the brake rotor from left to right, okay. The first face you selected is deselected in this operation and needs to be selected again. Click the corner of the view cube to reorient the model as shown in the image, then reselect the 8th face, okay. Click OK to accept the command and close the structural constraint dialog box, okay. So click OK, close the structural constraint dialog box, okay. So here the activity 3 summary we will see. So here in this tutorial, in this activity, we have changed the selection face priority. In the activity 2 we have seen select body priority. So here we are actually used select phase priority for priority to the phase selection, to make phase selection easier. Then next is practiced using different selection variations. Okay, so in the this is called as different selection variation. So that means select body priority, select phase priority, etc. Then next is apply fixed structural constraint in the x, y, z direction. Okay, when where the phases of 1/8 model variant meet the phases of the other 7 variants. Okay, so we have completed the activity 3. Then next is activity 4, apply loads. Okay, so we have to apply the loads. Okay, so first one is we have to apply a structural load of 13.8 megapascal to the uh, hub bore phase. So this is the hub bore phase. We have to apply 13.8 megapascal structural load to the hub force. Okay, so select structural load. So yeah, select, go to load, then select structural load, select this phase. Then here you can see that structural load set the type to pressure. So here you have to change the type to pressure. Okay, and you have to enter the value of the magnitude as 13.8 megapascal. 13.8 megapascal. 13.8 megapascal. Okay, then click OK. Okay, then so we have applied a pressure. Then next is apply a thermal load of 38 degrees Celsius, thermal load of 38 degrees Celsius to the same hub bore phase. Okay, select the thermal loads, then select apply temperature, then enter the temperature value as 38 degree Celsius. Okay, so go to this load, select thermal loads, second one. Okay, then select this phase, then one phase, then type is actually applied temperature, then type is applied temperature, the temperature value is 38, temperature value is 38, then click OK. Okay, so here you can see in the loads tab pressure, then applied temperature. Okay, then next is again go to thermal loads. Okay, then select heat source, apply a heat source of 36,500 watt per meter square Kelvin to the pad contact phase on a per unit area basis. Okay, so here go to the thermal loads. Okay, so go to the loads, thermal loads, then select this phase, then heat source, apply heat source. So apply heat source of 36,500. Okay, so here unit area, change this in the unit area, then watt per meter square. Okay, so watt per meter square 36,500. 36,500. Okay, then click OK. Then the next thing is apply convection load. So apply a convection load to all the faces that are exposed to ambient air, excluding the paired contact surface. Start by selecting all the faces of the brake rotor and choosing convection from the thermal loads. Then deselect the faces that are exempt. Okay. Go to the setup tab, select panel, selection filters, select through option is enabled. This option must be enabled to select faces on the backside that are hidden from the view. Then go to simulation workspace, setup tab, loads panel, thermal loads, then loads to convection. Okay. The thermal loads indicate that 93 faces are selected. Okay, so here you can see 93 faces are selected. The hub bore face is automatically excluded from the selection because it is already has a temperature load on it. Okay, then deselect the faces deselect the faces that are not in contact with air. Okay, remember the symmetry planes represent a slice through solid portions of the fully model. That is the brake pad contact face, heat source already applied, 2 faces on the XZ symmetric plane, 2 faces on the YZ symmetric plane, 8 faces on the XY symmetric plane. The thermal loads dialog should now indicate that 80 faces are selected. Okay. Then apply a 190 watt per meter square convection. So this is 190 watt per meter square convection to the remaining 80 faces at an ambient temperature of 25 degrees Celsius. Okay, and change the temperature value to 25 degrees Celsius. Okay, so we will do this activity. So go to the select panel, selection filters. Then you have to activate the select through option, enable select through option. So you can see this enabled, select through option is enabled. Okay, then simulation workspace, thermal loads, simulation workspace, thermal loads, then thermal loads dialog to convection, type it is, change it into convection. Okay, then click select the entire model. Okay, you can see 93 faces are actually selected. Okay, 93 faces are selected. Then you have to deselect these faces. Okay, so I will deselect these faces. Okay, so now you can see now you can see 80 faces. Okay, then you have to apply a convection value. Okay, so the convection value is 190 watt per meter square Kelvin. Okay, so enter 190 watt per meter square Kelvin value here. Then the temperature value to 25 degrees Celsius, the ambient temperature 25 degrees Celsius. Okay, then click OK. Okay, so here in the activity 4 completed the applied a pressure to the hub bore face to represent the mechanical load. This is the mechanical load caused by an interference shrink fit between the shaft and rotor. Then the second thing is applied temperature to the same hub bore face which is in contact with the water cooled shaft. Then applied a heat source to the pad contact face to represent the heat generated by friction during the braking. Then applied a convection load to all faces that are exposed to ambient air excluding the paired contact phase. Okay, so we have completed the activity 4. Then the next activity is solve the analysis and view the results. Okay, so you can run the analysis and examine the safety factor, stress, displacement, heat flux, thermal gradient results. Okay, you use the results to determine whether the brake rotor will yield as a result of the loads applied. Identify the areas of maximum stress. Look at different color transition options of the result. Explore the location of maximum stress. Explain the temperature distribution. Then animate the displacement result to see how the rotor changes with the use. Okay, so go to the setup tab, then solve, then click the solve button. Now we are ready to solve our, you can see the simulation model study 1 thermal stress. You have to solve it on cloud, then click here solve 1 study. Okay, so this will take a few minutes time. So you can see this is running. Okay, so now you can see job status. So that is the status. You can see this is running, the simulation is running. Okay, so here you can see the safety factor. This is the safety factor, then this is the maximum stress, then this is the heat flux, this is the heat flux, then this is the thermal gradient, this is the temperature, this is the temperature, maximum temperature, minimum temperature, then this is the displacement. Okay, okay, so you can see the result is completed. Click close. Okay, so here you can see the results. Okay, so you can select the safety factor, then stress, displacement, reaction force, strain, temperature, heat flux, and thermal gradient. Okay, go to the stress. You can see the maximum stress, what is 95.88 megapascal, and minimum stress 2.212 megapascal. Okay, so in this way you can conduct a thermal stress analysis in Fusion 360.